자, 네, 이제 시작하겠습니다.
Okay. Okay, so let's begin. So thanks for coming. So let me first apologize for the mistakes that I made in the last lecture. So I believe the slides will be shared later, and in the shared slides, these mistakes would have been taken care of. But basically, as we said, as I said in the last lecture, so someone pointed out that maybe this should be sine theta and cosine theta, and I changed those two. So that was wrong. So the sine theta should be cosine theta and vice versa. And also another mistake that I made was that there was in the amplitude amplification, there was this operator, which was R0 R psi, or maybe it's the order exchange. But if you apply this thing to that state, then I said this was sine 2 theta, but it's actually sine 3 theta, cosine 3 theta. And if you apply this n times, you get theta plus theta 1 plus 2n psi plus cosine theta 1 plus 2n psi perpendicular. Okay, so I just wanted to point that out. Okay, so I guess, yeah, you can download that. Okay, and today we're going to talk about qubitization. So just to recap what we did, we talked about LCU methods last time. And at the high level, what we did was the following. So our goal was to simulate e to the minus IHT. And what we did was that we broke that down into many little steps so that the norm of this thing in the exponent is order 1. And then what you do is that you expand this thing using Taylor expansion. And because without loss of generality, we can always decompose the Hamiltonian into sum of unitary operators. If we perform a Taylor expansion, that Taylor expansion will again be a sum of the unitary operators. Because if you multiply two unitaries, you get again get a new unitary. So you can do that. And then we showed that we can use two subroutines, one called select and the other called prepare, which selects the Pauli in the Taylor expansion and encodes the coefficients in the Taylor expansion. And with this, we could implement this e to the minus IHT divided by n with some constant failure probability. But I told you that this is okay because even if it fails with some probability, we can boost the probability to 1. So that's how basically the LCU worked. And qubitization can be thought as an, in a way, upgraded version of LCU. Now, LCU does have some advantages that qubitization doesn't have. For example, it is straightforward to extend LCU when the Hamiltonian is time dependent. But this qubitization, which I haven't told you yet, it's not entirely obvious when you what you would do if you have a time dependent Hamiltonian. So there are some pros and cons, but at least in most cases the Hamiltonian is time independent. And in that case, qubitization just outperforms LCU in so many different ways. And so you might wonder how qubitization works. So let me just tell you about the high level on how all of this thing works. So remember, our goal is, our beginning part is some microscopic Hamiltonian, like maybe Fermi-Hubbard model in 2 dimensions, or like an Ising model maybe. And our end goal is to synthesize this time evolution. So I have some time that I have in mind, and I want to implement e to the minus IHT. Okay, and the way this works in the framework of qubitization is that given the Hamiltonian, you first construct the analogs of the select and prepare operation that we discussed in the last lecture. But notice that here, like here, I said select parentheses H and prepare parentheses H, unlike in the previous lecture where it simply said select and prepare. And I wanted to emphasize that there is the H here because the select and prepare that we use in this lecture will be different. It is similar, but it'll be different than the select and prepare that we used in the last lecture. So select does the following thing. So I think it'll be good to compare what we did last time and what we're going to do this time side by side. So last time, given a Hamiltonian and some sufficiently small time t, we expanded this in terms of a linear combination of unitary. And from this, the select performed the following operation. For p such that alpha p is not 0. So if alpha p is 0, then you simply just don't care about those operators. And the prepare operation applied to a fixed state, like an all-zero state, it created a superposition state. So here I'm ignoring the normalization factor. So that's what we did last time. And what about this time? Make this a little smaller. So in this lecture, well, imagine expanding H, not e to the minus IHT, but H into a linear combination of unitary. And to make a distinction, I'll just denote the coefficients as alpha p prime, okay? And select H does something similar. As in the select, in that we apply this only for p such that alpha p prime is not equal to 0. And prepare that does the following, okay? So clearly they're doing something very similar, but in many ways you can see that the select H and prepare H is much simpler than the select and prepare for the Taylor expansion. Because for instance, let's consider a simple Hamiltonian, like a nearest neighbor Ising Hamiltonian. And if you exponentiate that and then Taylor expand it, then you obviously have terms which are not nearest neighbor. So like, for instance, if you, in the second order, if you consider H squared, you have lots of terms, and some of them will be something like, I don't know, Z1, Z5. So you get some like non-local terms, or you'll even get terms like Z1, Z2, Z4, Z5. And if you go to higher orders, obviously you're going to get more complicated terms. So compare that to just the select of H. In that case, you only have, if the sum is from I equals 1 to n, you only have n different terms, okay? So you can already sort of guess that the select of this form will be much simpler to implement and much cheaper to implement than the select on the left-hand side. And the number of non-zero coefficients will be much smaller as well. So also for the prepare, it's likely that we will get a reduced cost. So that's all very nice, but of course the question is, given these subroutines, how can you actually arrive at this end goal? And the qubitization, let me first remark that given select and prepare of H, you can straightforwardly construct what is known as the unitary encoding of H, which I will tell you soon. But qubitization is a process or an algorithm or a framework in which, given a unitary encoding of H, you transform that into this e to the minus IHT. In fact, it's more general than that. You can apply more general operators, which is a function of H, but Hamiltonian simulation is one concrete and very important application. So you might wonder why we're studying qubitization. And there are many reasons, but one reason is that it's the best state-of-the-art quantum algorithms for quantum chemistry applications. I think it's fair to say that in one form or another, the most recent developments on quantum chemistry, quantum algorithms for quantum chemistry is based on qubitization. And well, there has been many works, which all obviously are all different, but the framework of qubitization lives on in a sense that this framework of given a unitary encoding of H, synthesizing a time evolution is always the same. In these different papers, the different part is how to efficiently construct this unitary encoding. So the improvements are made on this side. So all of these works are like living in the world of qubitization, and this is and within that you're doing some extra optimization. And moreover, like if you view this like select and prepare as like black boxes, then qubitization is also optimal theoretically. And moreover, constants are actually quite reasonable. So it's theoretically optimal and it's actually practical, and especially it's the best for the quantum chemistry algorithms. So that's it's the best of both worlds. For instance, this is a table that I stole from a recent Google Groups paper, and actually Google Groups and their collaborators. And it looks like they really like making these tables. So what I want you to focus on is that it says primary algorithmic innovations. And you can see that starting from around like 2018, 2019, let's say use of qubitization. So this 2019 is an exception with the use of qubitization. And then it says tensor hypercontraction, but well, this is actually also qubitization. And in all the works that I mentioned right here, they always gave a new record for the efficiency of the quantum algorithm for particular, for certain very realistic molecules. So clearly, this is like the de facto standard for quantum simulation these days. Yeah, so I feel like a salesman for qubitization almost, but it's really that good in many respects. And another thing that is nice about qubitization is that it's actually flexible. So I told you that, well, and indeed, our main goal so far has been about implementing operators like this. But with qubitization, you can actually do other things as well. So for instance, you can apply this very weird looking operator. And you might think that this is a very strange thing to do and not a very useful thing. But it turns out that this is actually a very useful operation for the purpose of doing quantum phase estimation. So there are all these like new things that you can potentially do, and then you can like imagine the kinds of things that you couldn't imagine doing before. So it's also giving rise to new ideas. Okay, so we're going to learn about quantum qubitization. But before we do that, we need to first understand a much simpler problem. So the precursor to the qubitization is actually quantum signal processing.
Before you go on, may I ask a simple vocabulary question?
Yeah.
What is the reason for this choice of the word qubitization? What are you qubitizing?
Yeah, so it's maybe, yeah. I can give a technical answer. The the way if you look into how qubitization works, it you end up having a direct sum of two-dimensional subspaces, each of which behave like a qubit. And you're basically trying to synthesize the unitaries within these different subspaces. And that somehow gives rise to the end result of the qubitization. So it's, yeah, sorry, I don't know how to explain this better, but yeah, so I guess like you have to look into how it actually works to see, yeah.
Yeah, okay. I guess I will just wait and see.
Yeah.
Okay, thank you.
Yeah. So, yeah, let me first talk about quantum signal processing, which at first may seem like it is totally unrelated to Hamiltonian simulation, but we'll see its relations in the second lecture. In the first lecture, I would like to focus on this very simple mathematics. So now we're not talking about Hamiltonian simulation. We're talking about a single qubit. So we have a standard basis set, 0 and 1. And we're just going to use the standard Pauli operators. So let's recall that X is that. And we have a Pauli Y operator. And we have Pauli Z operator. And of course, they all anti-commute with each other. And if you multiply X and Y, that's, oops, IZ. If you apply YZ, it's IX, and ZX is IY. Okay, it's very simple math. And the problem that we're going to consider is the following model. So imagine you have a constant magnetic field in the X direction. So you have a Hamiltonian, and you have this term, and you have a time-dependent magnetic field. Think of it as like a pulse, like a burst of pulse, G of t times Z. And if you plot G of t, it'll look like this. So with periodic interval, you get a little bumps, which are like delta functions, and their height is proportional to, let's say this is psi 0, psi 1, sorry, phi 1, phi 1, and phi 2, and etc. Okay, and clearly in the limit that these pulses are infinitely narrow, you end up getting this time evolution. Right? So you have a constant magnetic field. So, and once in a while, you hit with this like a unitary operator that is generated by the Z rotation. Okay? So that's the physical model that we have in mind. And the main claim is that, oh, okay. So one thing that I forgot to mention is that I'm gonna make the spacing between the pulses as a constant. So that's why if you look at this, the angle theta for the x rotation, they're all the same. So they're all fixed to the same value of theta. Okay, and that'll prove to be important later. But for now, it's just a convention. Okay, and the claim is the following. The first claim is that if you have a product of operators like this, then it'll be a 2x2 matrix of a particular form. So on each entries, on the diagonal part, you have these polynomials of A, where A is nothing but the cosine theta. And in the off-diagonal part, you will have some polynomial of A and its complex conjugate times a square root of 1 minus A squared. Of course, this is like sine theta up to a sine. Okay. And moreover, these polynomials are not just some like completely random polynomials. They have a degree of at most d and d minus 1, respectively. And they have a even or odd parity. So if p is an even function, q is an odd function. And if p is an odd function, then q is an even function. The last condition is just a very trivial thing. It comes from the fact that all these unitary operators are special unitary operators, so their determinant must be 1. And that's just if you calculate the determinant of this 2x2 matrix being 1, that equation is precisely that. Okay. So that's
I guess D is the number of multiplications you do on the left-hand side.
right. Yeah. So maybe I should like point to this. Well, there are angles from phi 0 all the way to phi d.
Okay.
So there are a total of d plus 1 in, variable angles. Mm-hmm. Okay.
And the information regarding phi 0 through phi d, they enter into the coefficients of these polynomials.
Precisely. Yes, that's right. Okay, so we're gonna just show this actually. It's simple enough that it's good to work this out explicitly. So let's first consider the simplest case. So this is, well, okay. So focus on this equation. And now we're just taking d equals 1 case. So you truncate up to this. So you only have 3 terms. So we have that. And let's see what happens. So we have e to the phi 0, 0, 0, e to the minus I phi 0, and e to the I theta x is, you can verify later, is equal to I cosine theta plus I sine theta x. So this is cosine theta, I sine theta, I sine theta. And again, you have the diagonal matrix. And because cosine theta is A, I'm just going to replace cosine thetas by A and replace sine thetas by square root of 1 minus A squared. Okay, and then it's pretty clear. Well, we simply have A e to the I, that thing, I square root of n 1 minus A squared. And they're complex conjugates. And of course, A is real, obviously. Okay, so let's copy that. And first, just to make sure that we're on the same page, let's just copy that and compare this side by side. Indeed, we have a polynomial, P of A here, and we have its complex conjugate. And we have I Q of A, which I guess is just a constant here, times square root of 1 minus A squared. And here we have I times the complex conjugate of Q. So the form checks out, and degrees of P and Q are at most D and D minus 1. So here D was equal to 1. So P has a degree of 1. Well, it's a linear in A, so that checks out. Q, it's just a constant, so it's a degree of 0. That also checks out. And the parity is this is an odd function, and this, so this is an even function, okay? So yeah, very, very easy. Okay, and I'm gonna do this calculation just one more time, but for a slightly more complicated case. And the idea is very simple. The idea is that you view this middle thing as just product of two rotations. In fact, of course, you don't even need to choose these angles to be the same. Just break it down into sum of angles. And with that, we can express this matrix as P1, P1 star, I squared of 1 minus A squared, Q, I squared 1 minus A squared, Q1. So here I dropped the dependence on A. So P1 is really P1 of A, and Q1 is a Q1 of A. And this is just for convenience. So the first part, I guess this part will correspond to that. And the remainder, this will just correspond to another 2 by 2 matrix. I think I forgot the complex conjugation. And if you work this out, which is obviously, again, very straightforward, then you have this thing on the in the first entry, and then what you have is P1 I square root of 1 minus A squared, P1 Q2 plus Q1 P2 star. And you have their complex conjugated versions. Okay, so this case also checks out. I mean, it's kind of trivial, but let's just go through it one by one. So in the previous slide, we established that P1 and Q1 are, let's see, P1, Q1, and P2, Q2. They have degree of 1, 0, 1, 0. And if you look at the even or odd case, well, this was P1 was odd, even, odd, and even. So if you look at this term, first degree-wise, P1, P2 has a degree of 2, and 1 minus A squared times Q1, Q2. Well, Q1, Q2 is just a constant, and 1 minus A squared has a degree of 2. So this entire thing has a degree of 2. So that, again, checks out. And what about P1, Q2 plus Q1, P2 star? This is just a linear, well, Q's are constants, and P's are linear, just linear functions. So this is, again, just linear. So the degree is 1. That checks out. And here, now let's talk about the even and oddness. So here, P1, P2, that's a product of odd functions. So that's an even function. 1 minus A squared, even function. Q1, Q2, both odd, both even. So their product, it's again an even function. But here it's a product of two functions where one is even and the other is odd. So now you have an odd function here. So you can sort of imagine repeating this procedure many times to prove this claim recursively. And indeed, this is precisely what's going on. So let me just copy that here. Without loss of generality, well, the way this works is the following. So imagine let's say without loss of generality, we have broken down these sequence of operators into two pieces. Like the left part, maybe you want to cut it, maybe you want to break this down into e to the phi 1 z and e to the phi 1 z divided by 2. Whatever the case may be, you will have the product of this matrix and that matrix. And what you simply do is that you look at these entries and you just consider all possibilities. So, well, first of all, the degree is always easy because if you look at this, this entry, the degree of this entire thing is always degree of P1, P2 plus 1 minus a squared Q1, Q2 is for the P, if, let's say the degrees are D1, D1 minus 1, D2, D2 minus 1 by our induction hypothesis, this will be simply D1 plus D2. And what about P1, Q2 plus Q1, P2 star? Well, that'll be simply D1, degree of P1 plus degree of Q2, which is D1 plus D2 minus 1. And the degree of the second term is also the same at most. So you prove the first condition, and the second condition, you can just consider all cases. And that's, I believe there are like 4 different cases, and you just prove that it just works out. And then you have this last condition, which is a condition that is trivially satisfied by noting that all these unitaries are elements of the special unitary group. Okay, so this seems like a very straightforward exercise, and it is, but a non-trivial fact is the following. So what is not obvious is that the converse is true. So what we've shown is that if you have an operator of this form, that can be always written into this 2x2 matrix with polynomial P and Q, which satisfies these 3 conditions. A correct statement, well, a statement that I will not show is the following. So suppose you have a 2x2 matrix like this, okay, which you know satisfies conditions 1, 2, and 3. Yeah, and then there exists a sequence of angles, psi 0, all the way to psi d, such that this equality holds. Okay, so this is a converse statement. All right, so are there any questions so far?
Yeah, how would you prove it?
The honest answer is I don't know. I haven't looked into it very deeply. It's something, yeah, but in the Qubitization paper, there is a proof.
Okay, but in performing the converse statement, maybe the fact that the Q polynomial has a degree 1 less than the degree of the polynomial P, that might be a considerable restriction. Because then you're not writing down the most general 2x2 unitary matrix?
Sure. Yeah, there are restrictions. And also, I mean, they must satisfy this equality constraint. So that's another constraint. Yeah, so these are not completely arbitrary.
Yeah, then which maybe brings up the obvious question. If all the useful unitary operations are in the form shown on the right-hand side, then we can reproduce that by a series of pretty trivial Pauli rotations. However, not all unitary operations are of the form shown on the right. So then is it really that powerful?
I guess it depends on what you want to do. So, well, so far it's still a qubit example. So we can, I mean, let me first point out that for the qubit, you can already generate a arbitrary SU2 using this. It's like you have enough freedom to do that. But I think the real question is, okay, I haven't told you how this extends to qubitization, but I guess it's not totally crazy to think that some kind of polynomial like this will appear in qubitization. But then the question is like, is this kind of constraint be okay? And for the most part, they are okay because you end up not having to worry about Q of A. So what ends up happening is that you usually, it suffices to just think about P of A, and Q of A will end up being some like a junk that we don't care about. So in that sense, it's like pretty powerful.
Okay, so the expression on the right-hand side is in fact a general parameterization of an arbitrary SU2 matrix.
Yes, that's provided that you can choose A.
Okay.
Okay, and okay, so I realized that this might feel it's a bit, we're talking about something not so related to Hamiltonian simulation. So I feel like this is a good time for me to like tell you about the analogy. So at a high level. So what is shown above is the sequence of unitaries that I've shown for quantum signal processing. And what is shown below is a sequence of unitaries that we will use for qubitization. Of course, I haven't told you what this U of H is. At the moment, let me just say that it's some unitary that encodes information about the H. More precisely, U of H will be some unitary such that in some basis, it looks like the following. It will have a block diagonal structure. So the unitary will be on a 2n by 2n, will be a 2n by 2n matrix where the Hamiltonian acts on an n-dimensional hyperspace. And the z operators here, well, all right. So this is really that, and this is the same a single qubit z rotation. So so the similarities between the situation that we have in quantum signal processing and the qubitizations are twofold. One is that these parameters that define the operation that we want to implement, which in our case is the Hamiltonian simulation, is just controlled by a single qubit unitary. So that is an extremely simple operation. And there is a static unitary, which is just think of it as like an always on interaction. You have some unitary that you apply every single time. And that's just a fixed operation. So this is a non-local operation, but it's a fixed operation that you keep on applying. Okay? And therein lies the simplicity and the beauty of the qubitization. So in qubitization, it manages to compress the algorithm enough so that the entire algorithm just looks like a sequence of single qubit unitaries and some simple unitary that encodes some information about the Hamiltonian. Okay, so I guess this part was very brief.
Wait.
Yeah.
I think maybe you're going to come back to this, but
Yeah.
basically you're embedding a Hamiltonian inside as the upper left part of a bigger unitary matrix. So probably you're going to say this is always possible.
Yes.
And you're going to show us what the rest of the terms in the unitary matrix looks like.
Yeah, I will show what those other terms are. Okay. Although it's not too important what those terms are. Maybe I should mention that obviously unitaries are, they have a norm of 1, meaning that all their eigenvalues, because all their eigenvalues are e to the I theta, so their modulus is always 1. So obviously, if h is too large, if the norm of h is too large, then this is going to be actually impossible. So implicitly, what I'm thinking is that what I really meant was that this is h divided by norm of h, and in that case, so if you have an operator like that here, then you can always choose an operator, the remaining blocks, such in an appropriate way, such that u of h is indeed a unitary. Okay, so yeah, so I guess I'll have more time to talk about the qubitization, but I think for quantum signal processing, this is it. So what I wanted to show was that the basic math beyond quantum signal processing, which be related to qubitization. And I understand that this is just for a qubit, but we'll soon see that the lesson will extend more generally. Okay, so I would like to actually continue to the next lecture unless there is a question. And then have like take a short break in 15 minutes. Okay.